our tutorial is the topic of our tutorial is recent advances in visual domain adaptation and generalization. I'm Sheng Li. I'm Associate Professor of Data Science at the University of Virginia, and I'm happy to present the tutorial with two of my colleagues. One is Ronghang Zhu from the University of Georgia, and Dr. Xiang Yu from Amazon. And as you can see, the tutorial website URL is posted on this page as well. You can feel free to check our website to see the program of our tutorial, some slides, and also a list of papers which are very relevant to our tutorial. Unfortunately, we won't be able to present the tutorial in person due to some other concerns, but other personal issues. But we really want to share with you our thoughts and our recent progress on this topic. And we want to have more discussions with you and get your feedback. Please feel free to stop us if you have any questions. Okay, this is the schedule of our tutorial this morning. At the beginning, I will give a brief introduction to domain adaptation. In particular, I will mainly talk about the general idea about domain adaptation and some categorization of existing methods, especially what kind of challenges those methods want to address. And after that, Ronghang will give you a more in-depth overview of recent methods in domain adaptation. He will talk about several critical challenges which were addressed by recent methods and tell you how the methods will technically solve those problems. And after 9:45, we will have a coffee break of 50 minutes. And starting at 10 a.m., Ronghang will move to the next topic, which is from domain adaptation to domain generalization. And he will also present the differences between the two topics and discuss some methods in each topic. And finally, Dr. Xiang Yu will give us a very comprehensive review of interesting applications and especially discussions on future perspectives. So if you want to work on this topic and you want to look for some new research problems, new research challenges, then this part will be very important. Okay, this is outline of our tutorial this morning. I will start from the introduction to domain adaptation. I will have two parts. The first part is some background of visual domain adaptation, and the second part will be the overview of existing visual domain adaptation settings. I want to share some ideas from the very standard visual recognition task. As you can see from this page, assume we are trying to train a model, an image classifier, to do classification. And we have a source data set. In the source data set, we have images from multiple categories. This is very standard. And in most cases, those images are from the one single domain. This is a very standard setting. And a common assumption or a hypothesis is that we assume the source data and target data, they are from the same or very similar distribution. As you can tell from this figure, right? We have the distribution of source domain PS of X. X here refers to the images. And you can see the other distribution is PT of X. T refers to target data or test data. And those two distributions are very similar. And a benefit of this assumption is that if the data sets conform to this assumption, your model trained from the training data set will be easily adapted to the target data set. And you will end up with getting very high accuracy for classification. This is a very ideal assumption. However, in reality, we usually have the actual situation when the source data and target data, they are actually from different distributions, as you can see from this figure, right? So the source distribution is similar as before, but for target data domain, in this case, you can see some visual differences by comparing the source images and target images. Although they represent the same concept, the backpack and the bicycle, but this one is the images from real world, right? They have some background, they have some noisy on the images, but the target domain, in this example, we have images for the same visual category, but these images, they have quite different characteristics, right? They have different properties. For example, they have very clean background, white background, and this is an icon, not a real bicycle. Although they are similar and they are representing the same visual concept. So this kind of differences across the source domain, target domain, if you want to mathematically understand the difference, then they can be viewed as the difference between the two distributions, right? This is the orange one, represents the data distribution in source domain, and this is a blue distribution, which represents the target domain. Then in this case, it's very hard to train image classifiers which can do very well by only using the source data, right? Because it's a huge difference between the source and target data. So here is the motivation of visual domain adaptation. The goal is that we want to adapt the model from source domain to target domain and improve the accuracy in target domain. Before thinking about how to achieve domain adaptation, let's say if you train a classifier in a source domain, let's say we have a bunch of images for this class, for the class backpack, and the second class is for bicycle. We have a number of samples for each class. And for this binary classification task, you may have this classifier. This is a model learned from dataset. You want to separate two classes. If you simply and directly apply this model to your target dataset, you can imagine, right? So it's very hard to separate the two classes in target domain because they have different distributions. And therefore, if you look at the accuracy in target domain, it will be very low. And this kind of issue is mainly due to domain gap. Due to domain gap, you will see a difference between the source domain, target domain, and the difference between the two distributions. Therefore, the performance of the model in target domain will be very low. You may wonder why this kind of domain gap will occur in reality. There are many, many different reasons. So in general, you can think about the out of distribution scenarios, right? So due to various types of the distribution shift, such as covariance shift, meaning that the feature distribution from source domain, target domain are quite different. And concept shift. For example, you have 10 classes for training in your source data set, but in a target data set, you may have 11 or 12 or even more classes. So this kind of shift, we call it concept shift. And even more, you have some scenarios with temporal shift. Over time, the data distribution will be changed, right? So in general, all those things could be the cause of the domain gap. In particular, you can also see some concrete examples. Let's say the data collection methods might be different. For example, the images of same object, if you use different camera, then they will give you some different visual appearances, right? And also, if you think about the same person, as a person real ID as one example, due to different illustration, and sorry, this should be illumination and pose and color and background, right? Then those kind of differences will also cause domain gap between the source and target domains. And even more, if you think about image styles, real images versus simulation images, and even different cultural background and of the images, we have a lot of possible reasons for the domain gap. In other words, domain gap is a realistic and very challenging problem. So it doesn't make sense if we simply use the model trained from one simple source domain and we assume this model can work well. I believe every one of you know that it's very hard to have this kind of strong assumption in reality. Then the research question is, how could we address this domain gap and how to improve the model training? Then that's the major motivation for visual domain adaptation. The key is that could we be able to develop a better algorithm by training the model in one or more source domains and part of the target domain in order to reduce domain gap and most importantly, to improve the model's performance in target domain. If you look at this figure again, our objective is to somehow reduce this gap to make them well aligned and therefore the knowledge from the source domain, in other words, the classifier learned from source domain, can be well adapted to this target domain. That's the general idea behind domain adaptation. And domain adaptation is not a new problem. You may ask, okay, this is an old problem, maybe started for over 10 years. Why do you want to present this tutorial at CVPR in 2023, right? The reason is that although the standard setting of domain adaptation is an old problem, we also notice there are many different new settings in domain adaptation, which can be used in many realistic problems nowadays. So it's an older problem, but there are also many new flavors, many new perspectives we can think about and we can further develop. And meanwhile, more importantly, there are still many unsolved problems which will be covered in the last section of our tutorial. And that's why I want to give you a comprehensive picture of this domain to showcase, okay, how this domain evolves over years and what are the remaining problems. Here, I want to discuss the categorization of domain adaptation methods. First, there are many different ways to categorize methods, as in many different topics, right? So here we want to highlight two different ways to categorize those methods. The first way is to separate the methods based on the label space relationship between the source and target domains. And the second one is to consider the privacy issue you used when you do the adaptation between source and target domain. I will show you more details later. Let's look at the first one. So the label space relationship means that how do you assume the availability of labels in the source and target domain? As you know, in the visual domain adaptation, we have both source and target domain in training, that in most settings. Then the labels might be available, might not be available. Then how to consider that? Here we list in total 6 different settings by considering different types of label space relationship. The first one is the most traditional one, which is called unsupervised domain adaptation, UDA. And you can see some example papers as a list at the bottom of this page. In UDA, the very simple setting. So here I want to introduce this kind of notations first. So we use the solid circle to represent the source domain and the dashed circle to represent the target domain. And we use the solid symbols to represent label data and these empty ones to label unlabeled data. So we will use this kind of notations across this tutorial. Okay, for any model training, let's consider 2 different phases. The first one is training phase and second one is testing phase. During training phase, we have source domain and which are fully labeled. In most scenarios, we assume we have abundant images with labels for everyone. Here, for simplicity, we only show 2 classes. One is cross, the other one is circle, and they all have labels. And for the target domain, we also have a number of samples, but we don't have any labels. Then we will train the model based on the labeled source domain and unlabeled target domain. So the unsupervised domain adaptation, this term unsupervised mainly refers to the absence of labels in the target domain. But for the source domain, we still have labels. That might be a confusing part, but I want to clarify that. During the testing phase, we only focus on the target domain, and of course, we don't have labels. So the key idea is we don't have label for target domain, but we still want to train a classifier which can do classification in the target domain. Then here comes the major assumption. As you can see, we assume the source domain and target domain, they should have the same number and the same set of categories, right? So they both have 2 categories. They both have the category cross, category circle. That's why it is possible to adapt the knowledge or adapt the model from this domain to the target domain. Okay, then based on the understanding of UDA, there are many different variants of the domain adaptation problems. The second one is semi-supervised domain adaptation. Then you can assume, right? So previously we have unsupervised term, which refers to that labels are not available in target domain. But now in a semi-supervised setting, we assume we have a few labeled samples. As you can see here, right? We have only one labeled sample for each class, and meanwhile, some unlabeled samples. Then those kind of labels will be very helpful for training this model, because eventually the model will be applied to this target domain. So usually we could imagine the semi-supervised models should perform better than the unsupervised one. Then the next one is supervised domain adaptation. And this one is special because normally we assume we only have few samples available in the target domain. And if we are lucky, we have labels for them. Then the case is that we don't have to consider the unlabeled samples in the target domain. This is especially reasonable for some high-stake applications. You don't have access to a large number of samples. You have a few samples, such as in the medical cases, in the medical applications, but you will be able to get labels for those few samples. Then the issue is it possible? So given these few samples, you won't be able to train a very good classifier. But if you have a labeled sample set from a relevant domain, the question is, can you use the information from them and help you train a classifier for this domain? So in this case, the difference between this setting and the previous one is that we don't have unlabeled samples in target domain during training phase. For testing phase, they are the same as before. Okay, the next one becomes more interesting. In this case, we assume that, so this one is called partial domain adaptation. So sorry, this should be PDA. In partial domain adaptation, we have some assumptions on their label space, right? In this case, in the source domain, we have three classes: the cross, the triangle, and the circle. And we assume that the label space of the target domain is only a subset of the label space of the source domain. As you can see from this figure, in the target domain, we only have two classes, which is a subset of the classes in the source domain. And during testing phase, the label space is consistent as the one in the training phase for the target domain. So there's nothing special here. The main special part is that the source domain contains richer information than the target domain. This is also reasonable because in reality, let's say you have very unique problem. You only have a small number of classes, but you would have access to a large number of unlabeled samples from many classes. It doesn't make sense that every time you have to choose the specific classes to help you train the model, right? You may wonder, okay, I already have information from many more classes. Can it also be very helpful for this task, right? So the knowledge from multiple classes can be useful to train the classifier for fewer classes. This is assumption behind the partial domain adaptation. In other words, this setting reflects the assumption that the label space of source domain and target domain should be consistent. And that's one way, right? So we consider that the label space of source domain is larger than the label space of the target domain. If you think about this setting in an opposite way, this is open set domain adaptation. Here, we assume that, okay, in the target domain, we may have more classes. In my opinion, this setting makes more sense than the previous one, because when you train a model, you have fixed set of knowledge, no matter in terms of training data, the model parameter, or other problems, right? You have limited knowledge when you train the model. But once your model is trained, you want to deploy the model to reality. It is possible that the model will face some new scenarios, new settings, where new classes emerge. In this case, when you train the model, okay, you know that we only have two classes, and let's train this model. But it's possible that you may have, your model may observe new categories such as a star during testing, right? So the setting of open set domain adaptation is that we have more classes in target domain, and we want to ask the model to not only recognize the known classes correctly, but also reject the unknown classes. That's a very important capability for many AI systems, right? So the model should know when to work and when to stop working. That's why in the OSDA setting, we can do some manipulation of the data set to simulate some unknown class when train the model. Then we hope that during the testing phase, even though we have more classes which are not star, which might be other shapes, other classes, the model should be able to recognize the known classes during training, which are only two classes, right? And reject the classes which are not belonging to these two classes. So you can see we have more definitions of symbols here. The unknown classes as a star and the known classes as the cross and circle. And the last one I want to cover here is called universal domain adaptation. This one is kind of combination of the partial domain adaptation and the open set domain adaptation. So in terms of terminology, we assume that the source domain and target domain, they have a shared label space. And meanwhile, each of them has their own label space, or we call it private label space. In this case, you can see that each of the domains, a source domain has 3 classes. The target domain also has 3 classes. And they share 2 classes, the cross and circle. So we call them common class or shared classes. And meanwhile, this source domain contains a private class, the triangle, and the target domain contains a private class, a star. So, and during testing, in the testing phase, we mainly focus on performance on target domain. That's why you can see we have the same definition of classes as the target domain here. And this problem is more challenging because the model should be able to know which information will be helpful to train the model for target domain. In other words, the model should be able to do selective knowledge transfer. Not all the information from source domain are useful. You have to choose some of them. And meanwhile, you have to improve the uncertainty prediction capability of your model to not only recognize the correct ones, not only to recognize the known classes, but also to determine if the sample is from an unknown class or not. Okay, that's for the first perspective. We categorized the methods, the settings by looking at the relationships between the source domain and target domain. You can see we have a wide range of definitions for the problem. There are many new exciting problems to be solved. And on the other hand, if we look at the privacy issue, which is also very, very important issue nowadays, when we do adaptation, there are also some interesting definitions we want to share with you. The first one is called source-free domain adaptation. In this case, we assume that a model has been trained from a source domain. And in previous setting, we assumed that the data from source domain are available, and we can jointly use this dataset, source dataset, and the target dataset to train this model. But it is also possible in reality, especially due to some privacy concerns, the dataset itself is not available after the model has been trained. Instead, you may have access to the pre-trained model from source domain. Okay, so this is a very interesting setting because we cannot access the data or original data samples, but we can get access to this initial model trained from source domain. Then the problem is, could you also leverage information from the pre-trained model to help you do the transfer learning or domain adaptation for the target data set? That's why this is called source-free, because we won't be able to use the source data anymore. And the second one is actually an integration of federated learning and the domain adaptation, is FDA problem. In this setting, as you can tell from this figure, we have one server and multiple clients. For each client, it has its own data set, a small data set. And you can train a small model based on that, such as FS1, FS2, until FSN. We have N clients in total. Then the assumption is that we won't be able to share samples across these clients. right? Then how could you leverage information together and still train this model on server, which can be used to do classification for target domain? This is the setting of a federated domain adaptation. And the last one is called outsourcing training domain adaptation, OTDA. In this case, the idea is actually from the outsourcing model training, which is very popular and interesting in many cases. It assumes that the client, such as edge devices, they won't have capability to train model. So it's possible for them to outsource the model training task to a server, such as a cloud server, right? And meanwhile, due to privacy concerns, the client is not allowed to upload the dataset to a server. Instead, it's possible for them to construct a proxy dataset from the data available on server, right? In this case, we cannot upload data to server for model training, but we will be able to construct a very similar dataset from the server side and use the model parameters to help us train the model for this client. That's the outsourcing training domain adaptation. Okay, a quick summary for part one. We have discussed the general assumption and the main ideas behind the domain adaptation, especially some emerging problem settings in this topic. So as I mentioned earlier, domain adaptation is not a new problem, but there are many new settings existing nowadays, and they are very realistic and practical. And we also want to mention that privacy is a hard issue nowadays. So if you want to define a reasonable problem based on domain adaptation with some privacy concerns, then there are many interesting things you can do. And one more thing I want to mention is that auto-distribution generation is a very, very important aspect, especially for large model training. So we believe that ideas that have been developed for domain adaptation could be useful to achieve better OOD problems. Okay, that's for the first part. Do you have any questions? If not, let's move to the next part. You can see many details about the model, about ideas and the models and many discussions of existing methods. Ronghang will share some slides for the second part until the fourth part. Thank you, everyone.
Let me share screen.
Thank you, Shen, for your very wonderful introduction for the outline of those domain adaptation and domain generalization. It's very useful, I think. Yeah, so let's go to Ronghang for his part.
Okay,
sure.
Everyone can see the slides?
Yes.
Okay, so thanks, technique, for the introduction of the domain adaptation. Now, in this section, I will introduce some recent advances in domain adaptation. I mainly focus on some challenges in current domain adaptation scenarios. Yeah. So, for this part, I will introduce 3 challenges for current visual domain adaptation from the non-tail problems and the no prior label space knowledges, which is also corresponding to what Dr. Li has introduced the universal domain adaptation. And the last one is privacy issue problem for domain adaptation. So first, let's talk about the non-tail problems. Non-tail problem is common challenges in real-world application, especially take domain adaptation as an example for the source domains, which consists of many classes, but some classes may contain more data than other classes. So at here we can call those classes which have more data as the head class. And for those have less data, we call it tail classes. So in some real world application scenarios, we will find that the head classes and the tail classes in source domain will different from the target domain. For example, in source domain, the head class may be the backpack, But for target domain, the head class is the bicycle, while the backpack will become the tail classes. So if we still use the existing domain adaptation method to solve these non-tail problems in domain adaptation, this kind of method may be failed without consider the non-tail problems here. So the non-tail problem will introduce what we call the class imbalance problem, which will significantly influence decrease the performance of traditional domain adaptation in this real-world application scenario. So in this tutorial, we will introduce our solution for the class imbalance or non-tail problems for domain adaptation. The key idea of our work is based on diversify the majority classes, which are called the tail classes, because this kind of classes have this state. If we can enrich this part, they say to make the class imbalance dataset to the class balanced dataset, which would benefit the downstream task. And as we know that the classic mix-up by combine two dataset with the mix-up ratio together to generate the new dataset to enrich the count date is a simple and efficient way to enrich minority classes. But we know the drawback of the classic mix-up is that they use a fixed mix-up ratio. And this fixed mix-up ratio will limit the power of the mix-up. So in this work, one of the major contribution is that we try to propose a learnable dynamically adjusted mix-up ratio to benefit the class imbalance problem. So this is the whole framework of our PAT for the class imbalance domain adaptation. We can see that we have the labeled source state and unlabeled target date, and we use the mix-up to generate adversarial date to the model, and the hyperparameter lambda is the mix-up ratio. For the classical mix-up, the lambda is fixed, while in our framework, we mainly try to set the lambda as a learnable hyperparameters, and it will dynamically update with the model training process. And in this framework, we will have 4 loose items. For the L subscribe CA is called the central alignment, which will try to align the class center of the source and target domain by assigning the pseudo label to the target dataset. And LCE is the cross entropy nodes, which apply to the label source state. And IAS is also a cross entropy nodes, which apply to the what we generate adversarial dataset. And the LUDA is the existing UDA method, like the CDN or MDD or some other unsupervised domain adaptation method. So the key part is how to continually or dynamically update or learn the mix-up ratio lambda. So what we do here is that first we can do the mix-up with the initialized lambda here, and we only do the in-class mix-up because what we see that we try to enrich the in classes like minority classes diversify. So we prefer to use the in-class mix-up here, and we borrow the idea from the adversarial data optimization by set the lambda as a learnable hyperparameter, and we maximize across or modified cross entropy loss. The modified cross entropy loss will alleviate the problem of the graduate encoding or variation during the adversarial data learning. So, when we update the mix-up ratio and we feed it back to the mix-up process and update the generate X subscribe key ADV for the adversarial data generation. And after we get the update, the mix update, or we call it adversarial date, and we directly use the cross entropy rules to update the whole models here. And as we know that we cannot do the mixed up operation for all the classes, since we favor the minority class or the tail classes. So we set a hyperparameter, or we set a number pk here. Nk is indicated the number of samples for case classes, and nmax is the maximized number of data for the classes. And we set a random state which range from 0 to 1 if the random state larger than the pk, and then this corresponding case category date will do the adversarial date generation. In this favor operation, we can do more adversarial date generation on the minority classes, which will alleviate the class imbalance problems. So that's the main. And for the last part, as mentioned, that we also have the central alignment rules, subscribe CA, which try to align the class center of the source and target by assigning the pseudo label to the target domain. If we do not align the source and target and we directly do the adversarial date generation, maybe we may generate the data that cannot, they will fill into the other categories, which will get a negative transfer. So we have to do the domain alignment, like the central, what we do, the central alignment to alleviate this negative transfer influence. So that's what we do to solve the non-tail or class imbalance problem for the domain generalization. And for the next challenge for domain adaptation, we consider that the no prior label space knowledge. As we know that for the traditional domain adaptation is the unsupervised domain adaptation, which assumes that source and target share the same label space. While recently some new categories domain adaptation, like partial domain adaptation, they hold assumption that the source label space is include the target label space, while for the recent open set domain adaptation, they hold another assumption that the target label space contains the source label space. So for these three kind of categories, they need the private knowledge about the label space relationship between source and target. But in real-world application, we only have a source data set and it's full labeled. We know the label space, but we have a data come in. We don't know the label information of this unlabeled data set. What we can do? So that's the universal domain adaptation is proposed to observe this more realistic application scenarios. So in this application scenarios, we make a good assumption that the target and source domain, they may share some same classes like the circle and the forward and the path, and also source and targets, they may have their private class, like the source have the triangle and the target have the star. And then the task of the universal domain adaptation is to classify target dataset if they belong to the common classes, and they also have to identify those classes that not belong to the source label space, like a star here, and mark it as unknown classes. So that's what the universal domain adaptation want to do here. So to solve the universal domain adaptation, we propose the self-supervised based clustering strategies. So the main idea of our framework is that we have the source and target domain, and source is for label, target is unlabeled. And we also have a feature generator and a classifier if here. Specifically, we propose adaptive memory bag to store the target features for the self-supervised learning or self-supervised clustering. And specifically, we try to separate the target data sets into different areas. I will introduce the motivation later. So the key idea for our framework is that first, we have some previous work have shown that align target data to its neighbor would lead to a discriminative representation, which will benefit to improve the generalization of the model. And we should know that different target data should have different neighbors for align. And we also empirically find that consistent regularization would help improve the model's capability on unknown causes detection. So firstly, what we do here is that we propose the adaptive memory separation, which means that we separate the target data into different areas by depending on the entropy value of the target data. If the target data have a high entropy value, then the model's prediction is not reliable. So this kind of data set will have a high probability that belong to the unknown classes. And for the central part of the data set belong to the uncertain areas, that means the model may certain or may uncertain about this prediction. And this data may have some samples from the unknown class or some samples from known classes. While for the common area, which have lower entropy, which means that the model have high confidence about this sample's prediction, and this sample should have a high probability that belong to the common label service shared with the source domain. So with this separation, we will have a different kind of align strategy for the target data from different areas here. And then for the consistent regularization is quite simple, but requires the classifier to make a consistent prediction for each target set with the weak and strong argumentation. And this consistent regularization will help improve the model's ability on the unknown class identification. And for the one of the key part in our solution is that we have a different target neighbor for target data from different areas. So we can see in the middle figure here, if the target data come from the common area, so it will have a high probability that belong to the common classes as shared with the source. So this kind of data set, we only proved its target neighbor data set come from the common area and include the source cluster, and we push each common target data close to its neighbor from the common area, and the source syntax will help to learn discriminative features for the common classes. While for the uncertain area dataset, we will prove the whole dataset and include the source syntax as the neighbor to him to find the close one to close. While for the unknown area, this kind of data will have a high probability that belong to the unknown classes. So we only require this data to find its neighbor from the unknown areas, which will far from the common area, which will also benefit the model to identify whether the data from known and unknown. So to specifically how we compute, if for the alignment, for each target data, we compute the cosine similarity with the given neighbors, and with this output include the cosine similarity, we minimize this output entropy value. This will push each target data choose one of the neighbors to close. So that's the whole idea of our solution for the universal domain adaptation here. And the next challenge I would like to talk about is the privacy problem for domain adaptation. As we know that privacy has drawn a lot of tensions in many application areas nowadays. And basically, privacy will require the data and or label are only stored locally and cannot be shared with others. So basically, the constraint for the data privacy is that I cannot share data and model directly with others. How can we do the domain adaptation with the privacy issue here. So firstly, I would like to talk about the problems in privacy problem is that the source domain is not available for adaptation, which means that for example, if the source domain is a data collected by a company and this company spent a lot of money to maintain this dataset, so it's during that this kind of dataset cannot be made public. Instead of sharing the data, the company may release the model pre-trained by what we collected the data to make it public. So this kind of problem we can call it the source-free domain adaptation. We only have the source pre-trained model and the unable target domain. So the task is how can we efficiently adapt the source pre-trained model to the target domain without the source domain. It's a very practical and realistic application scenarios here. Here I would like to introduce one of the methods that have been also accepted by CVPR 2022. This paper combines the pseudo-enabling idea and the contrast learning idea to solve the source-free unsupervised domain adaptation. So firstly, they proposed a pseudo-enable refinement to get the more confident or more accurate pseudo-label for each target dataset. Specifically, for giving a target date here, and we can find its top key neighbors, and we can average the top key neighbors pseudo label as the final label to this target date, and this refined pseudo label will have a high accuracy. And to alleviate the negative influence, like the top key label is not accurate and will cause the final refined label is not correct. They also use the refined output to compute entropy value. This entropy value will serve as a weight to show how confident this refined label would be. And for the second part, they also adapt the contrast learning to learn a more discriminative feature space, but different from existing works like that. They maintain a memory bank like key to save the recent key samples as negative pairs. So here they propose a temporal square. They will record the past T predictions for each dataset. If a dataset pairs like the pink and the light blue here, if they show some labels or some labels appeared in the past and the same like for the beer and the beer for these two, and it shows that this kind of two samples will have a probability that they may belong to the same classes. In this case, these two datasets will not serve as, these pairs will not serve as a negative pairs. And based on these ideas, they can filter out some pairs that these two datasets may belong to the same classes, which will benefit the model to learn more discriminate features here. And finally, this framework will include three news items here. The first news item is the negative learning news, and the tilde Y is the complement label that randomly choose from the set of label, and the P subscribe SA is a strong argumentation of the dataset, and the second term is to prevent the posterior collapse, which is very popular that adopted in the source-free unsupervised domain adaptation. And last part is what we propose, what the paper propose the contrast learning, and their negative pair will come from the filter out by the temporal query here, and that's the overall loose term for the for this work. And the next part I would like to talk about is about the situation that when we consider federated learning, we have a multi-client and we and the data and the model learned in each client cannot be shared with each other. And when we have a new client come in, and this client only have enabled this state, how can we use count with what we have the kind to adapt the data, adapt the information, and to help the new client to learn model here. That's what that's what the federated domain adaptation try to do here. So specifically, we will have a n client which have a neighbor source domain, and each client have the computation powers to learn the model. And what they do is that they can share the during the training process, they can share the gradient to the new client. We can call it the target client, which is unable data, and they try to learn model that can perform well on the target domain. So the challenge is that first, the models and data are still locally, and they cannot share with each other. And there is the other major issue for federated learning here is that due to each source client have different dataset, the learned model will converge at a different space, will converge at a different rate, and which will make it more difficult to evaluate the contribution of each model here. And also, each source model learns feature is integrated, and which will lead to a negative transfer when adapted to the target client here. So here I would like to introduce a paper come from the engineer 2020, which proposed a federated adversarial domain adaptation to solve the federated domain adaptation problem. So in this work, this is a whole framework for this work. So on the top is the model for the source client, and lower is the
but when I started to create the group, the people from
sorry. Okay, so the lower part is the target client, and G is the feature extractor, and the DI is the domain identifier, which you can treat it as a domain discriminator, which is usually used in adversarial domain adaptation. And here they also have a disentangle part to disentangle the source feature into the domain environment and the domain specific features. And C and CI corresponding to the classifier. And R is a reconstructor to help reconstruct the features from the domain specific and the domain variants here. So firstly, to solve the privacy and the convergency problems here, to solve the privacy problems, they can share the gradients of each kind learned at the source domain to the target client. And meanwhile, to solve the convergency rate problems, they propose a guess statistics. Specifically for each learned models at source client, they can apply it to the target client, and then they do the k-mean cluster, like cluster the target data into k cluster, and they compute the L2 value of between each dataset that belong to the same cluster, which will evaluate the intra-cluster variance. And they propose a gain statistic gain like that compare with the previous iteration and the counter iterations get statistics. This gap statistic gain will indicate the dynamic weight of each contribution to the target date. And the second part is how to align the source and target domain. Here, they made the assumption that the domain identifier can touch both the features come from the source client and target client, and then this is a traditional adversarial domain element with a domain discriminator. And the last part is that they try to use the adversarial disentangle to disentangle the source feature into source invariant and source source specific features. And this source invariant feature will benefit the domain adaptation here. And specifically, they can first train the classifier C and CI, then they fix CI by, and only train the disentangle for the CI by minimize the entropy loss value here. And at the meantime, he also minimized the mutual information between the source invariant and source source specific features to help better disentangle the source features into invariant and specific. So that's what's the key idea of this this work to solve the federated domain adaptation. And the last part I would like to talk about is that when we consider a problem that if we consider the cloud and the client models, and only the cloud include the computing parts and the store parts, and the client only can collect data and store the data. They have no the computation parts to their model. And usually the cloud can collect plenty of data. Like we can see that we can treat the cloud include multiple source domains here, and the client is only a target domain with enabled. So in this kind of private issue is that we can use the cloud to use multiple collected data set to learn model, and we hope this model can generalize to the client. But as we know that the client data set cannot directly upload to the cloud due to a privacy issue, but somehow we can share some feature information with by add some DP noise to protect the privacy and update to the cloud. And this kind of update features can guide the cloud to snag some features that share the same distribution as the client. This snag feature can use it to their model, and this model should have a better generalization powers to the client. So this is the basic idea of this kind of private issue here. So for these problems, we call it as the outsourced training domain adaptation. This is work from the NIPS 2022. So the basic idea is that we have a cloud which includes a plenty of source data set, and most of this kind of data set is labeled. And then we have a client. This client can only collect unlabeled data set here. So what the sampling process do here is first they can use the model in the cloud to extract the class center features or the prototype features, and these prototype features can directly shared to the client. And we can compute the cosine similarity for each client dataset to the with each class center here, and with this kind of cosine similar values, so we can converge this score to indicate the cosine similarity of each class centers to the client, and then we can select those most similar class prototype. This kind of class prototype will have a most similarity distribution with the client, and then we can use this class center to guide the sampling to sample data and mimic the data in the client. This data set will use the train model, and then after train model we can deploy the model to client, and hopefully this kind of model will have a better performance on the client. So that's a key idea for the auto source training domain adaptation here. The key idea should be based on the data sampling. To make a summary here, so firstly, for the non-tail problem challenge in domain adaptation, we find that with a proper data augmentation, it will alleviate the class imbalance problems. Like what we do is that we improve the drawback of the classic mix-up, which only use the fixed mix-up ratio by replacing this fixed ratio with the learnable ratio. And then for universal domain adaptation, we find we should say that it should be closer to the real world application than other existing domain adaptation problems in terms of the open set. And in our work, we find that self-supervised learning is one potential good option to solve the problems. And for previous problem, we can say that it's very important in nowadays application scenarios. And for domain adaptation, based on different requirements, like what we have the source-free domain adaptation and federated domain adaptation and outsource trained domain adaptation, we can say that with different requirements, if we want to ensure the privacy, we should have different strategies to guarantee this kind of method can apply to the actual real world application. So that's a part for the recent advance in domain adaptation. Is there any questions? Okay, if there is no question here, then we will
Hi,
have
Rohan. So yeah, I guess I have one question. I rather say question, I think it's more like a discussion. So from your just introduced the materials for the domain adaptation, like you have also introduced several of those directions. Could you give us a brief summary about like there is federated domain adaptation, there is traditional like domain adaptation, there is this unsupervised domain adaptation. So from your perspective, what is the most important direction, or what are the most popular direction currently that people are focusing on within this domain adaptation area? Thank you.
Okay, thank you for the question. From my aspect, first, I think the source-free domain adaptation is quite popular from the 2020. And then a lot of work have pay attention on source-free domain adaptation because they consider privacy issue here. And for the federated domain adaptation, currently I didn't find as much works on federated learning as the source-free domain adaptation. So maybe federated domain adaptation still have some drawbacks here, because as we can see that take example for this ICNIL 2020 papers, especially for the domain alignment, as we know that the data in the client should be protected by the privacy. So the information from the source, the data information from source client should not be shared with others. Even though the target client, but as you know that in this work, they assume that the domain discriminator have the access to both the features from the source client and the target client. I think this assumption will somehow violate the privacy issue here. So in federated domain alignment, if for federated domain adaptation, especially for the domain alignment between the source and target without directly share this kind of either the image or their features to realize the domain alignment, I think it's still a problem that is unsolved here. And and
Yeah, sure.
also
Please go ahead. Yeah.
yeah, and also for currently, the outsourced training domain adaptation is quite very interesting, especially when we consider that we have a powerful computing server here, and if we want to deploy model directly to the different application areas, and due to the budget, the deploying budget, we cannot make sure the client has the power, and we can feedback the information from client like the convergence score to guide the server to learn model, and then deploy model to client to improve the performance. I think this direction is quite interesting, especially for the company which have a plenty of power, source power like GPU in their company, and they can only choose a cheap device that to the application areas, and this will also interesting. I think is an interesting direction for some real world application.
Thanks a lot for your introduction and explanation there. So I get that at least we can see very clearly, like privacy concern definitely would be one of the major direction, even within our domain adaptation or domain generalization field. So such as the, what you just mentioned, the federated domain adaptation, like the federated setting essentially try to localize each of those clients with its own data and separate it apart from the other clients so that the data cannot be shared and accessed from the other agents. So I think this is in the spirit of preventing the data leakage and protecting those privacy of those data. And similarly, I think that like one of the major and emerging direction within domain adaptation is the source-free domain adaptation. The source-free essentially mentions that like from the pre-training, you might leverage some of those data, which we call this as a source data. However, during your model development stage, you probably cannot leverage or access any more about this source domain data. So that is exactly this data privacy concern, such that we cannot access those data from the source domain, right? So yeah. I believe if it is, alongside what we want to convey here for the domain adaptation, then essentially source-free domain adaptation, I would see that it will be very, well aligned into the mainstream, and it actually reflects the main concern or the main interest of those research community from us. For example, the source-free domain adaptation has been receiving more than, many of those attention, and the works has been coming out from the top tier conferences consecutively, and
yes,
which is what we observed there. So yeah, so that's my understanding, and thanks a lot for sharing your thoughts here. Yeah, that's pretty much my question. Yeah, thank you.
Yeah, thank you for your question. So any questions? Okay, if no question, I think we can have a coffee break, and our tutorial will restart from 10 a.m.
Thanks, Ronghao, for your introduction and the recent advances in the domain adaptation introduction so far. And we'll try to talk to you back around 10 o'clock in the morning.
Okay.
Thank you, Ronghao.
Thank you. Hello, everyone. I think it's time to go to the next section for our tutorial here. So let me share screen. So for the next section, I will introduce about the domain adaptation versus domain generalization. As mentioned before, domain adaptation it's aimed to use the label source domain and unlabeled target domain to learn models that can generalize well to the target domain. And the main challenge for domain adaptation is that there is a domain gap between the source and target domains, which will significantly influence the model's performance on target domain. So how to alleviate the domain gap influence is one of the key direction for the domain adaptation. And also for the domain adaptation, we can find that as the evaluation task goal is unlabeled target domain, and during the model training process, they still need the access to the target domain. So consider some application scenarios, like if the model is not online or due to a data privacy issue, we cannot access the target domain. How can we solve this challenge here? So we consider the target domain may not available due to data privacy or real-time deployment. The model, we cannot have time to jointly using the target domain to learn the model. To solve this kind of challenges, another technique direction is proposed called domain generalization. In domain generalization, instead of need the access to the source and target domains here, the domain generalization only needs the access to the source domain. Here we can see during a problems, we have multiple label digits like the source domain 1, 2, and 2 other green. And we can use this kind of multiple source domains to learn model F. And hopefully, we wish this kind of learn model F can generalize well to the unseen target domain. And these problems will alleviate the drawback of the domain adaptation that they need the access to the target domain, and the domain generalization will have a better application scenario compared to domain adaptation, especially when the target domain is not available. So the key problem for domain generalization is that how can we learn the model that can generalize well to the unseen target domain, especially we have low private information about target domain, like the data distribution or label space here. So in my opinion, the domain generalization is a more challenging problem compared with the domain adaptation, since target domain is not available here. The following direction, I would like to introduce several domain adaptation categories based on either the number of the source domains, the label relationship between the source and target domains, or whether the source domain is full labeled or not. So firstly, the direction or category, we call it multi-source domain generalization, which is also short for domain generalization. It's the most popular one that have been researched by plenty of works. So for the multiple source domain generalization, during the training phase, we have multiple label source domain here. like the orange source domain, pink source domain, and green source domain. And during the testing phase, we use the model learned by the multiple source domain, and hopefully this model learned by this multiple source domain can generalize to the target domain. And recently, the assumptions that during a training phase we have multiple source domain is not available, especially, for example, if you try to solve a new problems, it's very hard to collect a plenty or multiple source domain, and then only when you face a situation that you only have one labeled source domain, can you learn the model that can generalize to multiple target domain here. As so based on this problem situation, the single domain generalization is proposed. As we can see that during the training phase, we only have one label source domain, which is not as diversified as the multiple source domain generalization, since they have multiple source domain. Compared with the single source domain, only one source domain cannot generalize the model as the multiple source domain here. So, and also during the test phase, the learned model need to evaluate under different type of different kind of target domain here, which will have a high requirement for the model learn at the train process. So in this kind of source domain generalization, one of the mainstream technology is to adapt the data adaptation. The key idea is try to diversify the single domain generalization, and with the enriched single domain, this dataset can learn the more generalized model, and hopefully this model can perform well on the multiple unseen target domain here. And the next category is that consider the open set problems in the multiple source domain generalization. Since we cannot guarantee that every collected label source domain share the same label space, sometimes each source domain will have their private categories. For example, for the first source domain, they have, for example, there are multiple source domain here, and the circle category is shared over all source domains. We can call the circle one as the common class is shared overall. And also we can find that each source domain will have their private category, like the first domain have the triangle, and the second have a star, and also for the testing phase, the target domain also have a private classes. So the goal of this open set multi-source domain generalization is try to use multiple source domain to learn model that not only classify the target datasets that belong to the common classes shared with the multiple source domains, but also identify those classes that is unseen in the multiple source domains label space. And the fourth categories for the domain generalization is the open set single domain generalization. Compared with the open set multi-source domain generalization, in open set single source domain generalization, well, we only have one source domains, and we have multiple target domain, and the multiple target domain will include the unseen classes in the source label space. So the problem is more challenging compared with the open set multi-source domain generalization, since there is only one single source domain generalization. There would be two tasks for these problems. First, they should have to learn or generalizable models that can generalize to multiple target domains here, and also the model should have the ability to identify the categories that is unseen in the source label space. And the last category of the domain generalization is called semi-supervised multi-source domain generalization. Since maintaining or full labeled multi-source domains is quite impractical in some real-world application scenarios, but collect plenty of dataset is quite easy, and we can pay some cost to label to label some part of dataset for this collected source domains, and then these problems will become that we have multiple source domains here, and each source domain, they will have plenty of unlabeled dataset and a few labeled dataset, and the goal is still that we utilize multiple source domains to learn model, and this model should be generalized well to the unsafe target domain. So for this semi-supervised multi-source domain generalization, there would be two challenges here. First, we only have few short datasets, which will make the label information is not as good as the traditional multi-source domain generalization. And how to utilize those unlabeled source data is very important. It can prove the distribution of the whole source data set, and with this few labeled target data set, a few labeled source data set, can we learn or robustness or generalized model that can perform good on the unseen target domain. So here I would like to introduce some traditional methodology for domain generalization. So basically, these three kind of technology are quite popular for solving the domain generalization problems. The first is meta-learning. So in meta-learning, as we suppose that we have multiple source domains, and the target domain is not accessible during the training process. And we also know that there is a domain gap between the multi-source and the target domains. How can we alleviate the domain gap is the key problems for the domain generalization here. And for meta-learning, they have a meta-train and a meta-test. And for this, for the meta-learning for domain generalization, they borrow the ideas that they can split the multiple source domains into meta-train part and a meta-test part. As we know that there's still existing some domain gap between among the source domains. So by dividing the multiple source domains into meta-train and meta-test, we can mimic the domain gaps. And by using the meta-test learning framework, we can alleviate this mimic domain gaps to learn the model. And hopefully, this learn model can have the ability to generalize well to the unseen target domain. So the key idea for the meta-learning domain generalization here is that we should separate the multiple source domains into meta-train and meta-test, and the meta-train and meta-test, there should be exist some domain gap, and so that the whole training process is push the model to overcome this kind of domain gap. By overcome this kind of domain gap, I think this model should have ability to also somehow alleviate the domain gap between the multi-source and target. And this kind of model should have a better generalization on the unseen target domain. And the second technology for domain generalization is the data adaptation, especially for the single source domain generalization tasks. So basically, the data adaptation is that either they can use the most simple and efficient mix up to enrich the source domain, or they can use the GAN, or they can use the argumenter to change the styles or generate new dataset to enrich current source domains here. For example, this work adversarial teacher-student representation learning for domain generalization, they design an argumenter to enrich the source domains, and they adopt the two steps learning strategies to either learn the argumenter or learn the models. And by these two steps, they can learn a better argumenter to generate more enriched or more diversified data to the source domains. And based on this kind of data augmentation, the final model will have a better generalization to the unseen target domain, since they have seen plenty of data include those augmented sources. So that's a key idea for the data augmentation. And the other one for data augmentation is the self-supervised learning. So the early self-supervised learning is that we can propose some prediction tasks and combine it with our object tasks. For example, in this domain generalization, they based on the main task, like the object classifier, they try to classify the object. They also split it each image into a patch, and they do the perturbation for each image and shuffle this sub images, and the subtask for this kind of self-supervised learning is that they should to giving the shuffled images, they should to predict the perturbation of this shuffled image, and by adding this kind of self-supervised learning strategies combined with the main object tasks, it will benefit the model to learn more generalized feature embedding or generalized feature embedding, and this generalized feature embedding would benefit to the unseen target domain here. So that's all for the domain generalizations part. So any question about this section? Okay, if no question, I will get into the next part here. In this section, I will introduce some recent advances in domain generalization. Yeah, for this part, I will introduce 3 challenges for recent recent development method of the domain generalization here. So first is about open set for domain generalization. And for open set domain generalization, I would like to introduce 2 subsections. First is about open set for multi-source domain generalization. And second one is for open set single domain generalization. So let's first get into the open set multi-source domain generalization. For open set multi-source domain generalization is that we have multiple source domains, and those source domains, they have their private classes. Each domain has their private classes, but they also have a shared classes. And for the unseen target domain, the unseen target domain will have a shared classes with the multiple source domain. Meanwhile, they also have the unseen classes for themselves. So the tasks for the open set multi-source domain generalization is that the model should classify the target dataset into the exact category if this dataset belong to the shared category, shared label space with the multiple source domains, either or identify this dataset as the unknown class, since this classes is this dataset is belong to unseen classes. And for this purpose, the work open domain generalization with data augmentation meta-learning, they propose this framework is based on the meta-learning, like they have from the right side to the left, from the upper right side to the left, upper left side to the right side. This is the meta-train part, and from the bottom right side to the left side, this is meta-test part. So for this work, the key idea will include the 3 parts. First is data augmentation. They try to enrich the the source state distribution, and also they adopt very popular meta learning strategies to solve the domain generalization, and they also adapt to the knowledge dissemination to better adapt to the weight here. So first, for the data annotation, this work is also for the idea from the classic mix-up. So firstly, as shown in this figure, we can see that for the classic mix-up, it only mix up the two samples. So the Jarrett mix-up data will stay along the edge of the triangle. This kind of classical mix-up cannot significantly enrich the diversify of the source domain. So to alleviate this kind of problems, this paper proposed a draw mix-up. This draw mix-up is that they will mix up samples from multiple source domains. By this operation, we can say that the mix-up data will cover the entire triangles data here. So for this work, they will consider two kinds of mix-up directions. First is feature level mix-up. That means they will mix up the features from different source domains. And the data level mix-up, that means that they will directly mix up data before put the data into the feature extractor. So let's get the details of this framework. Since this work will learn the multiple models, learn the feature extractor and classifier for each source domains here. For example, if we have m source domains, then they will learn m feature extractor and classifier. And here we take the s source domain here, and here s equals to 1. So it is the meta training loss function. They will have 3 items here. The first item is the basically input the first source domain with the constant entropy loss to update the feature extractor and the classifier. And the second term, which will include the mixed up dataset, which come from the data level and feature level to both learn the feature extractor and the classifier. And the last part, we can see that there is a Y distill, and this Y distill is the soft labeling that come from other source domains learned model prediction. We can see that actually this is the mean average over the its models prediction and the other models prediction. And after the meta train process, then they will use the gradient to update the temporal model G bar with the GG and the GFG, and this update model will serve for the meta object. We can also call it a meta test. So for meta test, the input data is not the I source domain. Instead, they will input other source domains except the S source domain. This dataset will also have 2 kinds of input here. The first is the orange dataset, like the second and the third source domain dataset to update the F and G, and also the mixed up part. The mixed up part will include the mix up will only include the feature level mix up, and specifically we can find that they do the proposed dual mix up at the meta train and meta test. But as we know that in the details, if for example if they do the dual mix up at the meta train, then the mix up ratio of the I dataset will have a higher percent during the mix for the mix up dataset, and for the meta object mix-up, the ith domain will have this percentage. It's the mix-up dataset here. And finally, when we compare to the gradient from the meta object, then they will go back to update the models at the meta train strategies. And this is a whole train process for this work. And to evaluate the models on the target domain, first they will compute the output for they will compute the probability of the target data belong to each categories in the source neighbor space. And meanwhile, they will also have entropy that if this kind of this predictions confidence is less than the threshold, then they will mark this target dataset as unknown dataset. Otherwise, they will classify the target data into one of the categories in the source neighbor space. And for the next open set problems for domain generalization, I will step into the open set single source domain generalization. This is our work in Acnear 2020. For open set single domain generalization, it's more challenging because at first it's as mentioned that first it should be solve the diverse. It should be neural models that have the ability to generalize to the multiple target domain, and then they also have faced the open set problems. So in our empirical study, we find that currently existing single domain generalization methods, they cannot handle the open set single domain generalization problems. So in this work, our framework will have two stages. The first stage is that at the maximization stage, at first we also brought the idea from the existing single domain generalization that we can generate some dataset X subscript key to enrich the diversity of the source domain, and then we can also generate some exogenous dataset X subscribe U to mimic the unseen classes. And at the minimized stage, one of the goal is that we try to use the generated dataset X subscribe key to improve the generalization of the model. And meanwhile, we also use the exogenous dataset X subscribe U to improve the model's capability on identify the unknown classes. So to be specifically, first, we need to at the maximization, we will generate two kinds of datasets, the X subscribe U and the X sub K. The X subscribe K will merge to the source domain since it's the diversity of the source domain, and the XU will help to improve the capability model on the unknown class identification. So for the generalization of X subscribe K, we directly adapt the idea from the single domain generalization, like this two kind of papers adapt the adversary data annotation to enrich the datasets. Since the goal of our work is improve this kind of method on open set problems. And here we can see the loose subscribe ADA is what they propose loose to generate the diversity classes, and subscribe concept is to restrain the distance between the orange data and its diversified datasets is kept into a range, so that the generated data still have the same semantic meaning compared with the orange data. Well, for how to generate exogenous samples, here we here we adapt multiple binary classifier. For example, if we have C categories, then we will have C binary classifiers. So the key idea of our auxiliary samples generalization is that we, as we have a multiple binary classifiers, we try to push the, for example, if the dataset is for example, if the data is belong to the first category, then the goal of our generalization is to push this sample far away from the first category, and meanwhile we increase its probability that they belong to other categories. In this how this kind of dataset will far away from its original category, which may belong to other category, or it will belong to some unknown classes, so that the auxiliary datasets can not only enrich a diversify of the source domain, but also can mimic the unseen classes here. And after we have the enriched dataset X subscribe K and our auxiliary dataset X subscribe U, the optimization at the minimization stage will include this 4 noise items. The first items is the cross entropy noise that apply to the X subscribe S dataset, and the one with or loss function is applied to the X subscribe S, which used to train the multibinary classifier. And the third loss item, the binary entropy loss, is applied to the X subscribe U, which will force each auxiliary dataset either belong to one of the categories in the binary in the known classes, or keep it as unknown classes. And the last term is the cross-class regularization, which means that for each auxiliary dataset, they will have a probability for the binary classifier, and also have a output come from the multiclass classifier. Since the multibinary classifier has a ability to identify the unknown classes, which have been proved by some previous works. So we can require the consistent regularization between the multibinary classifier and the multiclassifier by convert the multiclass classifier's output to the version of the multibinary classifier. With this regularization, which will improve the multiclass classifier's ability on unknown class identification. So that's the basic idea for the open set single domain generalization. And for the next challenge in the recent domain generalization is about the privacy issue. As we know that privacy issue have been proposed for domain adaptation, so they should be also met in the domain generalization here. Let's see. So for privacy issue for domain generalization is quite simple here, since we have multiple source domains. So each source domains will be stored at the local client, and this client have a computation power to learn the model. And at the same time, to keep the privacy issue, the model and the data of each client cannot be shared with other client models. And the goal of the privacy issue for domain generalization is that they should use multiple clients to learn a model, F in the blue, and this model can generalize to the unseen target domain. So in this direction, we can call this direction with the federated domain generalization. And previously, to solve the federated domain generalization, they have the basic framework that they can share the hyperparameter or gradient of each client which store each source domain, and by average this upload the hyperparameters, they can average them to get a new theta, and this new theta will lead to a model learned at the server. And the drawback of this kind of global objective is that they may focus on unbiased train strategies, but it cannot guarantee the generalization to the under the domain chapter. That means if the server dataset will contains the domain gap with the dataset in the client, in the source client, then the average parameter learned model in server will performs not well, and also the each domain contribution, or we can call it the each client contribution to the global model is not equal. So maybe some client dataset will have more similarity or more same distribution in the server. Then this kind of the contribution of this model to come from this client should have more weights, so that the model can have a better generalization to the unseen data here. But a drawback of the federated domain generalization, or challenge of the federated domain generalization, is that the target domain is unavailable during the model learning process. So we cannot find which source domains will have a higher similarity with the target domain. So in this paper, they make assumptions that the global model, if they have a fair performance among all the domains, that means the global model have a similar performance among all the domains, then maybe this model will have a better generalization for the unseen domain, since the model is fairness. So the generalization of this model should be better than the previous model which will prefer which will perform better than some domains than other domains. And also this method propose a learnable hyperparameter alpha, which can dynamically adjust during the learning process. While compared with previous method, the parameter P is fixed during the training process, and also they try to improve the generalization adjustment by the assumption that the fairness performance, which will guarantee the model's generalization. So to be specifically, the learn object of this model is include two items here. The first item is the empirical risk on the dataset of the model in the server, and the second is the generalization gap. The generalization gap is estimated between the global model, since the alpha with the theta is summarized to indicate the model in the server, while the theta subscribed to I indicates the I source domain learned model's empirical risk. So the generalization gap is indicated is estimated between the generalized model and the local model with their empirical risk. And we can see that alpha controls the balance between the reducing the global risk and enforcing the fairness among the generalization gap. And we can also find that the hyperparameter beta here beta is when beta equal to 0, then the new global objective will become to equal to the previous global objective. And if the beta equal to infinity, that means the beta is very large, then this optimization object will make the generalization equal, since they will make each the generalization gap equally. And also, fatness on the local cannot guarantee the fatness over the model with this kind of generalization gaps here. And the next step is that how can we adjust, how can we update or adjust the alpha here? In this work, they propose a linear average change for the alpha hyperparameter. The R indicates the currently communication epoch, and the R-1 indicates the previously communication between the client and server. And still we can find that there is a generalization gaps here. And this generalization gap is estimated between the current global model and compare with the previous model. And this will indicate the contribution of the this will indicate the fatness of the service model to each client, and this will also guide the adjust of the hyperparameter alpha here, and the mu is the mean values over all the clients the generalization gap compared with the counter models and their local private empirical risk. And the D is the linear average change of the hyperparameter. R is the totaling number of the communication between the server and the client. And after they update the hyperparameter and they readjust this hyperparameter alpha to 0 to 1, so that make sure the sum of alpha equal to 1. And this number hyperparameter will benefit the model to learn a fat, or we can call a fatness model on each domain, each source domain, and then with the assumption that this fatness performance will have a better generalization. And the last challenges for recent domain generalization I would like to introduce is the unsupervised learning for domain generalization. This we have found that self-supervised learning or unsupervised learning have show advantage in main tasks like domain adaptation. So similarly, in domain generalization, unsupervised learning should also have the ability to improve the generalization of models. So in these challenges, they redefined the domain generalization problems. Here, first, they will have multiple unlabeled multi-source domains, and they still have some labeled dataset. Maybe this labeled dataset shares the same distribution or different distribution with this unlabeled source multi-source domains, but this few short and the multi-source dataset will have different distribution with the unseen target domain here, but this labeled dataset will have the same label space with this unseen target dataset. So the whole training process of this problem is that first they have to apply the unsupervised learning method to pre-train the model. With this pre-trained model, they use this label dataset to fine-tune this pre-trained model. Hopefully, this fine-tuned model have a better generalization for this unseen target domain. So first, the model is pre-trained with a unlabeled dataset, and then this pre-trained label should be fine-tuned with the label dataset so that it can deploy it to this unseen target domain. And the key part of this unsupervised learning for domain generalization is that they care how pre-trained affects the model generalization ability. So in other words, they would pay more attention on the unsupervised pre-trained learning part here. Where for fine-tune part, they can use several existing domain generalization methods to fine-tune the model. So for this direction, I will introduce the very recent papers in CVPR 2020. In these papers, they will have several models here, and we can say these two red models are feature retractor, and this blue model is designed to predict the domain label of each dataset, and the input of this domain predictor is the low-level features that from the feature retractor. And the upper part, the similar loss is the cross entropy loss, which will train the domain classifier to have the ability to identify which domain the given image belong to, and the and the lower part, this two feature retractor is used to get two kind of feature representations with giving the same dataset with different like the weak and strong augmentation. And then they will have also designed the contrast learning by considering the domain information. So firstly, the baselines for this work is that they can directly use the influence induce to pre-train the pre-train feature retractor with the multiple unlabeled source dataset. But this kind of pre-train will fail due to they fail to consider the domain information. So this work will address this drawback of existing unsupervised learning method, like the influence induced here. So as described that this part is for domain classifier, so it's trained with cross entropy induced with a domain label. And the second part is that they have a domain parameter unsupervised learning. This is also still based on the influence E, but we find that there is a parameter W subscribe N and D here. N is indicates the indicated number of the of the image. For example, the nth image with D indicates the probability of the nth image belong to this domain, and then the DQ indicates the and also here we have for example, if we have D source domains here, then for each source domain we will maintain our memory bank to store the recent like key features as a negative samples. So for example, for example, with the n sample that belongs to these domains, and we can compute its positive pairs similarity, and also we can evaluate its negative pairs from all the target domains by go through all the featurebacks QD. D will enumerate from the 1 to the D, and also the hyperparameter W will evaluate this kind of control learning, so that this loss will considering the domain information here, and beyond the this refined supervised learning process, they also considering to enrich or increase the hardness of the negative samples by adopt the adversary data annotation, which is quite popular in the single domain generalization, by treat the data as the update tensors and maximize the loss, like maximize the loss come from the domain classifier to make the to increase the hardness of this kind of negative dataset. Okay, so that's all part about the recent advances in domain generalizations. is there any questions here?
Hi, Ronghang. Similarly, for domain generalization, you have introduced several of those very representative of those works, and thanks a lot for your introduction. And some of them you might also go into the detail of those optimization and their framework design. But let's go back to the high level again. So for those domain generalization, could you try to highlight a little bit more about what are several of those major directions alongside the domain generalization, such that the people are actually focusing on those most promising directions?
Yeah. So from my aspect or from my understanding, the most promising domain generalization aspect right now, I think you should consider privacy issue and the open source part, because currently there are only few works have been pay attention on the open set purpose in domain generalization, like for open set multi-source domain generalization and the open set single domain generalization. For my knowledge, I only find 2 papers that specifically address these two methods, but we can also find that there are some other open set learning methods that can directly evaluate the performance, the open set performance, but they didn't they didn't do specific design for this open set for the open set purpose in domain generalization. So I think the open set part is still promising because there are still limited works that pay attention on that. And second part is also still related to the privacy issue. As mentioned that for privacy issue, we have several privacy definition, like we can only share the data we cannot share data model, or we can only share the model. Some parts, but it will depend on the application, the details of application stereo or requirement. So with different kind of application requirement for privacy, we will have a different design of the privacy issue method for the domain generalization. So from my understanding, I think privacy issue in domain generalization still have a lot of work to do, depend on requirements from the privacy requirement, like high level or low level. And the last part, the unsupervised problem for domain generalization, it's a quite new problem. It's proposed in last year CVPR 2022, but in this work, they still have several drawbacks. One of the most drawbacks is that the proposed method only, the proposed method only consider domain information to pre-train model, but in their implications, actually the W will become to either 0 to 1, and then they will become to the in domains. How to say it will the proposed domain irrelevant unsupervised learning will finally become in domains self-supervised learning. For example, they directly apply the info to the each domain to learn model instead of considering the connection between each domains to guide the unsupervised learning. So I think the unsupervised domain generalization part still have a lot of work to do.
All right, thank you so much for sharing your information and also your insights alongside the domain generalization part. I appreciate it a lot. And yeah, so that's my question.
Okay, thank you for your question. So let's go to the last part, the applications and the future perspectives, which will be introduced by the Dr. Xiang. And so, yeah.
Thank you, Ronghang. So let me try to share my screen and from my side, and let's continue for the last part. Finally, we go to the last part. let me know if you can see my current view here, especially
Yes.
when I come into the full screen there. Okay, thank you, Ronghang. So the last part is the application and future perspectives. To make a quick recap, in the morning, we actually started from a very wonderful talk from Professor Shen Li. He has introduced the introduction to domain adaptation as well to cover some part of those recent advances in domain adaptation. Then Ronghang actually further take up the more kind of tasks to cover the most of the parts for the related works about both the domain adaptation as well as the domain generalization. And further, he tried to compare the differences between the domain adaptation and the domain generalization, and then following up with the recent advances in domain generalization. And in between, we have also have several very interesting discussions regarding the high level trend about where are we going for domain adaptation, as well as what are the major directions for the domain generalization. And lastly, let's see what kind of those interesting applications alongside domain adaptation and domain generalization can bring us to the plate, and what would be the potential future perspectives that we can further looking into. With that being said, there are two major sessions that I'm going to cover. The first one is talking about some of those very representative applications besides the image recognition that Ronghang has just covered. And the last part is the future perspectives that I would like to share and discuss with all the audiences and the participants in CVPR. So the first is the applications besides the image recognition. Here I try to divide the current domain adaptation and domain generalization into those four main categories. And forgive me that there will be many more of those applications, but due to the time and the space limit, we can only cover a limited several of them. And with that being said, there are four major directions we would like to discuss about. The first one is the action recognition. The second one is the semantic segmentation. Third one is face analysis. And the last one is the medical applications. Let's firstly touch base about the action recognition. I would like to introduce two of those most recent and representative works. One is called this multi-model domain adaptation for action recognition. Let's directly go into their general framework. From the setting, they assume there are multimodality, such as they just mentioned the multi-model into their overall framework. One is the RGB channel for the general one, the well-known, the image channel. And the second modality is the flow channel, which is they try to pre-extract those flow and motion information as a second channel for the input. And then from those two streams, and alongside each of them, they will try to apply this adversarial alignment kind of efforts denoted by the loss of the discrimination for the RGB channel and the alignment loss for the flow channel. And they will try to target at aligning the source denoted by those blue arrows to the target denoted by those red arrows for each of the modality, including both the RGB and the flow modality. And then after that, they will set up the contrastive learning loss, which is that because they know they have the resources about, both from the sources of those image data and the target from the image data, as well as the source and target from those flow data. So in this way, they will naturally form those positive pairs that come from the same category, but across different modality, or comes from the same category, but across different domains, and form a combination of those four pairs of those contrastive learning losses together to form this stage of those penalty. The third one is a very canonical classification loss, because for this action recognition, presumably you will try to define a set of those preset categories, such as punching, such as running, such as archery, etc. So all these kind of action labels will be predefined there, and try to associate each of the input to each of the concrete action category, so that you want to encourage this category to be maximizing the likelihood of that even input image and the output label there. And combining all these three stages together, that is the general overall framework for this MMDA framework. And we can see from their framework, they very smartly to utilize the two modalities between the RGB information and the flow information, as well as they try to very wisely to set up the contrastive learning across different modality and across different domains. Then we want to introduce a consecutive another work, which in the high level, the framework shares certain similarity, but there will be also certain very significant improvements from the MMDA to the CMDA. Here is the CMDA overall architecture, and presumably there will be a source and a target. The source means like you will pick up one of those initial data set as your training data, but eventually you want to apply your model or your AI solution to a targeted environment, such as the RGB videos from a different scenario, right? And secondly, naturally, this video kind of application will involve multiple modalities. That is where they termed as the cross-modality application here. And similarly to the MMDA, we have both the RGB information as the image modality or video modality, as well as the flow or motion as another modality. And here we clearly will get 4 of those data points, data angles there, like the source RGB, the target RGB, the flow source, the source flow, and the source target. So here the problem actually is defined as the cross-modal contrastive learning, as well as the cross-domain contrastive learning. Each of the tasks is trying to align the cross-modal representations and the cross-domain representations respectively. And here is a more detailed overall diagram from their proposal. So starting from the inputs of both the RGB channel as well as the flow channel, there will be 4 streams, as we just discussed for those 4 data point corners. And they will set up 2 streams similarly as MMDA. One is RGB encoder, the other is the flow encoder. And there will be 4 lines of those features from the source for the appearance, features from the target for the appearance, features from the source for the motion, and features from the target for the motion as the inputs. And then from the feature space, initially we will have 4 different data points denoted as the solid circles, the solid crosses, the dashed, the empty circles and empty crosses there. And for the first stage, different from the MMDA, like directly apply those adversarial alignment across different domains and across different modalities. Here, they differently to propose this projection head, which is denoted as the lowercase h, for each of those 4 data streams. And then within the same within the same domain, denoted as the same color for each of the blue lines and the green lines, they will try to propose this kind of the contrastive learning laws within each of the domain. This is the cross model, but within each of the same domain of those penalty there. So that is for the first stage. And then they come into the penalize of those cross-domain information. And this time they try to maintain those data stream as within the same modality, but across different domains. Say they will try to introduce those like the laws for the appearance as well as the laws for the motion separately. And we take actually the form of those appearance laws and the motion laws are quite similar. We just, for example, pick this laws for the appearance as example. So they will collect those features such as those feature of source within appearance and feature of target within appearance, penalized for each of the modalities, such as the image modality and the flow modality separately. And lastly, similar as MMDA, they will try to penalize from those supervised information by providing those action labels together with the inputs of each of the individual video clips. So combining all these 3 sets of those losses together, they try to propose a kind of cross-model and cross-domain solution to deal with this very complicated setting of those video application here. And then let's take a look into the similarity and the dissimilarity across these 2 very representative video action recognition applications. So firstly, we can see that video source is a very typical scenario for domain adaptation because it will naturally leverage a lot of those different modalities and different domains. For example, video naturally contains multiple modalities, such as the video, motion, audio, text, etc. And the video scenario is challenging because it will contain a large amount of those variances across both modality and the domains. Then talking about the difference between the MMDA and CMDA, we know that from our introduction of the framework, CMDA actually uses projection head to directly penalize the cross-modality difference. But from MMDA, they actually utilize in a very traditional and canonical adversarial alignment from across two of those modalities, both the appearance and the motion for each of those source and target. Secondly, the CMDA uses contrastive loss for cross-domain alignment, while MMDA utilizes the adversarial alignment there, as we just introduced. This is so far for the application for the video action recognition. Feel free if you have any kind of question in between, so I will try, more than happy to answer each of your concerns or comments there. If not, then we move to the second session, which is semantic segmentation using domain adaptation and domain generalization. Let's take one of the very representative work from Volpe and Murino. It's titled as Addressing Model Vulnerability to Distributional Shifts over Image Transformation Sets. So from their assumption, let's look into this image as an example. On the left-hand side is the original input. And they say, due to certain assumptions, such as in natural, we can encounter a lot of those color jittering, the camera vibration, all these kind of variances. And they try to summarize this as a kind of content preserving transformations, denoted as T. And they assume that both in the natural real world as well as this hypothetical kind of setting, there will be a set of those family of those content preserving transformations. And they, from their criterion, how to evaluate whether one of those solutions is robust and generalizable across different of the scenario is that given a well-trained model, try to test across this both original input as well as the outputs from all these kind of content preserving transformations to see if the results are stable or not. And indeed, as shown in this example, so from the author, they actually try to show that if the model is trained based on only the original input on the left-hand side of the image, and then directly testing with all kinds of those content preserving transformations, clearly they observe that for a bunch of those areas, actually the prediction from the segmentation results is not so stable. We can see within the highlighted ellipsoid, some of those regions are very ambiguous actually. So how to solve this kind of problem? Here is their proposal. So based on the assumption that in the real world, there will be a innumerable set of those transformations, and each of these transformation, you can regard it that after that transformation from the original input, you will try to introduce a new domain from comparing to the original input domain. And your model needs to generalize across all these domains so that the model performance is robust, right? So their problem actually is further converted into how to select out the most optimal set of these transformations, such that when the model further jointly trained with this combined several of those domains, including both the original domain and those content preserving transformation processed domains. And in this way, the final model is claimed as domain generalizable. And their central task is try to conduct the search among the predefined set of the family of those transformations. And in their work, they further try to propose this random search as well as the evolution-based search to find out most optimal and ideal subset of those transformations from their predefined sets to optimize the overall loss as denoted above to achieve the best performances. And finally, from the results, such as the visualization on the right-hand side, you can see that the indeed succeeded in mitigate those ambiguous segmentation zones, such as the traffic light area. And for this part, I feel like indeed, so across different applications such as video action recognition and close to this semantic segmentation, or across this visual tasks, indeed, domain adaptation and domain generalization can bring us a certain level of the insights to mitigate those real problems there. And here, the central idea is that how to search the optimal transformations and optimal, the leaded transformation leaded domains for the optimal generalization for the model training. And then the third main area that we want to introduce as the representative works for those applications of domain adaptation and domain generalization is face. So here, I believe there are also a set of those very representative works. And sorry that due to limits of the page and the space, we cannot list all of them. So let's just pick one or two of those most representative ones in the literature and just try to showcase that indeed DA and DG are very useful in all kinds of these applications. For this face recognition problem, essentially the definition is that given that usually we will have a set of those high quality training data, like we can try to, from our lab environment or from our very finely built up of those capture system, we can get a bunch of those high quality input images. However, for our real application, usually you can imagine that the condition cannot be well controlled due to this and other constraints, such as we might encounter the street view of those pedestrians, but we still want to satisfy certain kinds of surveillance tasks. And during that very challenging situation, we might encounter those large head poses or with very low resolution of those images. Or sometimes the human faces might be occluded with all this kind of natural and unnatural obstacles, such as cabs or some kind of those people over people. And there will be also a lot of the other unnameable of those factors to be involved. And clearly, if we just train the model utilizing the very clean data, can we imagine that how well this model can be directly applied to those very challenging real situation unconstrained testing data? The answer is very, very clearly that it's not so possible or feasible to directly achieve so. So here, domain adaptation, domain generalization again becomes very important. And let's firstly see how the traditional approaches target this problem. In general, so if firstly given several of those proposals, such as to deal with those large pose variation or the low resolution problem, or as well as the occlusion problem, the traditional way is try to set up different models, such as denoted across this model 1, 2, 3, 4, etc. Each model will separately to target one or very limited number of those variations denoted. And in this way, we know that they are actually still the domain adaptation kind of approaches, which they will require this target domain data to be involved into the overall training, as well each of the model, when you further try to ensemble across all those models, you may encounter a very large scale of those model complexity issue after the ensemble. So what's our solution, or what we want to target the problem from our perspective? So we want to build up a generalized single model to resolve as many of those variances as possible. And how are we achieving this? So let me briefly introduce the detailed implementation for this new novel pipeline there. The very canonical and the important approach and step is that we believe if only utilizing the very clean input data is hardly to cover the large variances of those real application situations. So because of that, we novelly try to introduce several of those data augmentation approaches. Some of them might be very common to the audience, while some of them might also require a certain kind of non-trivial implementations. For example, we try to target as three main axes. One is the blur. And we know that blur might be as simple as the Gaussian blur, but sometimes it might be as complex as a cannot be simply estimated by any kind of a single kernel. And second one is the occlusion. Similarly, the occlusion pattern could be very vulnerable, while in the meanwhile, the occlusion objects or the foreground can also be quite different from one to the other. And the last one is the head pose. We believe these three main of those axes are the most, can cover the most, such as 95% of those variances appear in those current literature of those face-related data sets. For the poses, it's actually very non-trivial because we need to model the whole face geometry and then try to manually and, you know, in a kind of optimization way to rotate the faces with the harmonic and the best visually looking of those appearances from the facial area. And with these all techniques combined together, we say we can achieve kinds of towards flexible control of the facial appearances in aspect of those blur, occlusion, and poses. The right bottom of the showcase actually indicate that we can, in a very large range of those variances, we can cover those facial variances and try to approach the real and the realistic variances from those face data sets. The second step is that we send in both the original input and the augmented inputs into the backbone and extract the feature embedding. Here, different from the traditional methods, we try to separate the original holistic embedding into multiple groups. Here, it's because based on the observation that utilizing a single holistic embedding actually is a little bit hard to incorporate and cover the entire variances that we just introduced from the variation augmentation. And we found that practically, if you try to set up several of those groups and let each of the group of those sub-embedding from the holistic feature to deal with one specific of those variation, such as we try to separate to the first group to deal with the occlusion, the second group to deal with the blur, and the last one to deal with the pose. In this way, we can provide a more flexible, the embedding learning to deal with different of those introduced variances in between. And we indeed observe that with this kind of sub-embedding section, we can try to observe even much lower training losses during the face recognition training. From the loss side, here we also try to introduce this uncertainty aware or confidence aware of those penalty identification losses there. So the high level idea is that usually the trusty and the confidence from those clean and high quality images are actually much more trustable comparing to those uncertain ones. Like the more confident ones denoted as a bigger or the larger size of those circles, while the smaller ones are indicating for those uncertain and with very poor quality of those face input images there. So if we try to equally treat the importance of all those samples, and naturally we will encounter a kind of a biased model estimate. And how to mitigate that? Here we try to propose that let's try to assign the weights for those samples from different situations, such as high confidence samples and low confidence samples with different weighting. We try to trust more towards those confidence samples because we know that in natural, the high confidence samples with higher quality of those images will lie more closer to the center of that individual, of their identity. And in this way, we disregard a certain level of those importance from those poor quality data points, and then hopefully we will have a more robust and less biased estimate of those prototype or the class centers for each of those identity in the feature space. Lastly, we want to further regularize this embedding to be more slim as well as efficient. So how to achieve that? We observe that for each of those group embedding denoted in different colors, such as green and blue, each of them will in charge of a different variation. For example, we observe that the sub-segments of those embedding in charge of blur and in charge of occlusion, they may have a large of those correlation. We want to further regularize these sub-embeddings to be incorrelated to each other such that the representation could be more efficient. And in this way, we try to penalize the correlation of those sub-embeddings across all those defined sections so that the regularization can further penalize the correlation to be smaller. And eventually, we also observe that the recognition performance can be further boosted a little bit more. After talking about this UR phase for recognition, there will be a lot of many other phase-related analysis, such as the phase anti-spoofing. So what does phase anti-spoofing mean here? The task is essentially try to target the problem of that, given a face image, you can imagine that the face image can be from a real face is captured from your camera, or actually can be redisplayed from your cell phone as a photo to the camera. So this is very essential as the prerequisite for many of those applications, such as face recognition. In a kind of surveillance system, you do not want the others or the fake of those images to bypass your face recognition system, and maybe a very severe of those privacy related issues might happen. So this will be very important, especially for those surveillance situations there. So given that background here, what is the detailed problem setting here is that suppose you will have the fake images, which could be regarded as those second redisplay of those faces, right? And you will have your real images, which is directly capturing some of those benign faces. And eventually the task is try to conduct this binary detection or binary classification to tell whether if that face is originally or genuinely collected or actually is redisplayed. And they will try to set up this kind of feature generator for both the fake faces and the real faces in two streams, denoted by different color as the purple and green. And then after the feature normalization, so their assumption actually is that for the real faces denoted in those green zones, although we will see that from different camera types, from different cell phones, from different the instruments or the devices, the capturing of each of those real faces might also appear a certain kinds of differences, such as the color tone or the different pitches, etc., right, from those histogram of those RGB information. However, they think that internally they will show a certain high consistency across all those real images, because physically your faces with those skin material is kept consistent across different, no matter whether you change to a different type of those camera. However, for those fake ones denoted in the purple region, the variance could be huge. For example, you might imagine that you actually are redisplay from your iPad with a very poor lighting in the indoor scene, and the other might be utilizing a completely different devices, such as I don't know, maybe it's from a laptop or etc. So the variances across different screen of those redisplay actually can be quite larger than the variances from the real faces. And based on this assumption, they propose this asymmetric triplet losses. So where they want to push all those real images from different domains to be as close as possible to each other, while trying to separate apart all those fake images away from this centralized real image corpus. The second one is pretty straightforward. So both the real and fake images will send to the classifier to conduct the cross entropy loss for the supervised binary classification task. And lastly, they want to align as exactly as try to push all those real faces all together. And this is achieved by the adversarial alignment losses there. They set up a domain discriminator as what they call as a single side adversarial learning, because this single side lies in that they only care about those real faces to be well aligned, while leaving the fake faces with a larger of those cross class and within class variances large enough there. So if there is any question, just feel free to raise here. So for the phase anti-spoofing, I believe this is one of the very state of art and achieved the top performances, especially in the tasks of that train on one single source or train on several of those source domains, while directly testing on those blind target domain. And from that perspective, they have achieved very leading performances in the literature. Then we can see that from the phase applications, we see that data augmentation is one kind of those very important tool that can provide multiple domain data for the domain generalization strategies there. And secondly, attention and weighting across several of these different domains are very important to combine those multiple source domains data. In terms of both in the appearance domain as well as in the feature domain. For example, the appearance domain, we actually can recall the mix-up as one of those very canonical and very successful approach there. While in terms of the feature domain, we actually achieved, like for example, this several of those phase anti-spoofing all are operating from the feature domain. And similarly, mix-up can also apply from the feature domain. And last one is that the generalization can be inspired from some invariant properties, such as in the phase anti-spoofing application. A very interesting and inspiring assumption is that for the real phases across different domains, they still assume that they can share the same feature subspace and try to align them and push it towards to be as clustered, as close as possible there. Okay, so let's go to the last application, which is also a very fundamental and with a large potential and future perspective of that, which is the medical applications. So medical actually is also besides the computer vision, medical is a very important and large area that a bunch of separate field people they are looking into. But as inclusion and the work completeness, we want to include them into our discussion and see how domain adaptation and domain generalization can be leveraged into the medical domain. And for the challenges in medical imaging, we can see that due to the different modalities, such as from those CT images or MR images, they have a T1 phase and T2 phase, and each of these phases, they may not share the commonality and appears with a large of those domain gaps there. And similarly, from this MR and CT, we clearly see that, for example, the color tone, the gray scale, or the magnitude are quite different from one to the other. And similarly, there will be the other factors that will cause this kind of a domain differences, such as that, for example, from those CT image, if the instrument actually are capturing the same organ from different angles, then still it will try to show the same organ from different views, right? And this will be another example that showing the different imaging parameters to achieve this kind of differences there. The third one is that like you will see like across different patients, because of those each individual's specificity, and those images could be quite different even from the same angle and same view of the same organ. While similarly, like due to recently there will be the generation kind of technologies involved into our pipeline, you can clearly see that with the current technology, the generated images could still appear to be quite different from the real images. And due to all these kind of factors, we can see that even within the medical domain, the problem actually exists quite common, and where domain adaptation and domain generalization is quite needed there. So that's firstly look into one of the very typical application, which is utilizing the domain adaptation to deal with the, like for example, the eyeball or the vessel segmentation kind of problem there. And on the left-hand side, the definition is that we have the source data, which is the labeled eyeball images. We have the target data, which is the labeled X-ray images for the same of those eyeballs. And there will be also a portion of those, the data from the target domain, which is unlabeled, completely unlabeled. So from this SS-CADA framework, the authors try to introduce a kind of encoder-decoder structure. For those labeled source and labeled target, they try to propose this kind of a very novel of those encoder and decoder structure, and then they try to mitigate those source and target in the middle of those feature maps together, denoted in those the orange of those source and the blue of those target on the top of those images together. So they will try to apply the supervised learning loss, denoted as LS, to conduct the segmentation task. Well, the key step actually is how to deal with those unlabeled target domain data, denoted in those purple links. The pink links here. So they try to in the second stage, Firstly, there will be an exponential moving average of those teacher model as the distribution signal for the current self-embedding mean student kind of training there. And in the meanwhile, they will discard the source domain of those feature maps while try to replace it with the newly filled in of those unlabeled data. And the hypothesis is that the unlabeled X-ray data with this certain kinds of those domain adaptation happened in the first stage, they should share a certain overlap of those in the feature space comparing from this unlabeled X-ray data together with the source of those labeled data there. Yeah, that's essentially the high level approaches to solve this kind of vessel segmentation task in the medical domain. And let's try to recall a bit about what is the limitation in the current domain adaptation for medical imaging. So we can see that there will be this pre-defined of those target samples. The model will need to leverage the target domain data. Well, at some kind of those settings, you cannot access of those target domain data due to the, for example, the patient's privacy related kind of factors there. And in the meanwhile, we need to leverage certain kind of those target domain data to define the adaptation task. The other thing is that, so as we similarly see in the face applications there, so one model might be only target at one of those target domain data. And if you just simply apply those ensemble of those models, you might also encounter the bottleneck from those capacity of those models. And you cannot easily to deal with those multi-site data kind of settings for the medical application tasks there. And indeed, connecting to the domain adaptation, due to this kind of a set of the challenges there, so the researchers also try to leverage domain generalization into the discussion about solving those medical problems there. The multi-site data, actually, you can regard it as that the data from different sites, that all the hospitals. And there will be different imaging protocols and scan vendors to capturing those the medical images there. There will be also the unpaired data sets with various intensity distributions, and it's hard to align manually or even just try to index from those, the different hospitals, the different time of the same instruments. It's the overall kind of a human annotation is kind of too huge. So if there is some kind of automatic way to overcome this kind of domain gaps and try to learn a more robust and consistent feature presentation to conduct the tasks such as the medical segmentations there. And let's briefly introduce one of another work from the same group of this GU 8L. So from their work, they try to propose this specific architecture design for the domain generalization. And in their design, there are two main components. One is the domain composition, the other is the domain attention. So from their inputs, they assume a multiple of those different domains of those feature maps actually are set in the parallel, denoted as different colors of those blocks there in between. So there will be this domain representation bank denoted by B, each of P1 of input F, P2 until Pn. These are the features with respect to each of those different domains from the same inputs. And then they try to propose a kind of domain representation, the linear combination of those different domain representations. In this way, they will further introduce the domain attention, which is the input from the same source, and this will try to find out the correlation across different of those domains and try to highlight the correlation while also try to de-emphasize the insignificant of those correlations among different feature presentations. And finally, we try to combine the feature representations from different domains as a unified feature for the final task. So we can see that they will try to learn towards unified representation across multiple of those domains. And eventually this unified representation will work well, hopefully to work well back to each of those individual domains. So in that way, they try to achieve this kind of generalization. Okay, so for medical application, we also introduced two representative approaches. One is from the domain adaptation, which also we analyze several of those limitations from domain adaptation. And then further, we introduced a more generalized mechanism, which is the the domain generalization kind of approach to deal with the medical image segmentation problem there. And from that, our take home is that the domain adaptation can effectively mitigate the domain shift caused by different imaging sensors, modalities, etc. However, domain generalization could be better to deal with those multi-site problems where data are located distributed from multiple different hospitals. And lastly, cross-domain representation learning and domain attention are inspiring generalization approaches, such as we just leveraged from this kind of architecture design there. And indeed, from their report, they have achieved the cutting edge performances comparing to the state of the art of the same in the same domain in the same field of those domain generalization approaches in the medical segmentation tasks there. All right, so please feel free to block me or just raise your questions. So far, we have touched base about 4 main directions of the applications leveraging domain adaptation and domain generalization. For the last session, we would like to initialize some discussions about the future perspectives in this field. However, it's not limited to that. We just want to inspire our thoughts from the community, and hopefully that the more researchers and the professors can lead can guide the whole direction and those emerging discussions about the new fields and the most promising directions there. The first perspective is that we gradually observe that there is one chain of leveraging the foundation models. The foundation model actually is a very hot topic recently, such as the very well-known GPT-3, the ChatGPT, the GPT-4, which achieves the latest, the cutting edge of those performances in multiple different tasks, as well as the open source, the Llama, which is so far the biggest open source, large language model in the literature from Meta. So there are a lot of those applications based on this, open source and the release of those large language models to conduct a series of those cross-modality and computer vision, natural language processing, and the other areas of those research and industry productization. So let's firstly look into the high-level concept of those foundation models. So for foundation models, essentially you will imagine there are 2 encoders or 2 streams of those data flow. One is from the text encoder or the language model. So this language model, you can imagine, is trained with a super huge scale of those, like the vocabulary of those data. And this language model, we essentially can conduct a wide range of those tasks, such as say you provide us a set of those paragraphs or set of sentences there. The language model will return the summary based on the text understanding and the summary of those whole paragraph. This is the text summarization. And it will also, you can imagine the language model can bring you a feedback such as the answer. This is the text question answering to those based on the text inputs and overall we can see that the large language model actually has a super strong capability to understand those semantics from the text level inputs, as well as to make the very reasonable and mimicking the human level of those summarization and logistical thinking or reasoning to provide those feedbacks, right? So from the large language models, we know that it has been achieving new levels of those cutting edge of towards the understanding of those texts. And while from the vision domain, we know that we, of course, due to the development and success of those convolutional neural networks, the transformers, etc., we also try to refresh and bring in the performance or the understanding of those visual signals to the new cutting edge levels. However, we still can see that if merely based on a single visual channel, our understanding towards the image, towards the video, are still kind of limited only to the visual channel. And we clearly see that it's harder to arrive at the understanding and reasoning level. However, the text side, the language model actually has certain kind of signal to show that it's already been capable to approach at the understanding and reasoning level. And CLIP actually is the first and pioneering work to close the gap, hopefully to leveraging the strong semantic understanding capability from the text model, from the large language model, to lift up the understanding from those visual models. And they try to utilize a very successful and very canonical way, which is try to contrastively learning the visual embeddings towards its corresponding positive pairs of the text embeddings. And hopefully that from the feature space, these two domains of those embeddings can be aligned from one to the other. And by leveraging this kind of very inspiring work from CLIP, from OpenAI, we want to see that from our applications can be similar to utilize the text channel with the very strong understanding as well as reasoning capability to guide us for the vision channel tasks. And let's pick one of the domain adaptation approach that has been utilizing some pioneering efforts to try within this vision and language pre-training kind of direction. The work is from GER ETAL. They try to conduct the domain adaptation from the prompt learning. So to introduce this framework, firstly, we see that from the left-hand side, which they try to denote the very canonical and traditional domain adaptation, which is that given a source domain and target domain of those images from different domains, you want to train a backbone or feature extractor denoted by F. And eventually at the latent feature space denoted by Z, you want to correctly classify the label Y hat, given that trained on the source domain, but expecting that the target domain data XT can be correctly to be classified as the correct label of the Y, right? So we see that this traditional framework do not leverage any kind of additional channel or additional knowledge and information. And from their proposal, following the spirits of this leveraging the foundational language models, they try to propose the text embedding and the text encoder denoted as the G in the middle of the right-hand side figure. So in this way, naturally, they try to propose a set of those prompting kind of technologies, such as this is a sketch of dog, this is a photo of a real dog, etc. Kind of this prompting dictionary into the pipeline. And then this prompting will provide a certain richful bunch of those variances within the input for the text domain. And then from the text embedding, they can set this as a bridge or the anchor point to guide the alignment from both the source domain data inputs and the target domain data inputs, and further extract it into the latent variable of the embedding domain as ZS and ZT. So let's take a further look into their design of those prompting engineering. For example, in this figure, we can see that the domains actually incorporates a wide range of those different categories, such as the art domain, the clip art domain, the photo domain, and the product domain. And they actually are very smartly to design this kind of prompting engineering into three parts. The first one, what they call as a domain agnostic kind of prompting. So here you can see that this kind of prompting is irrelevant to any kind of those domain related information, such as an image of, a picture of, a sketch of, etc. This is discarding about any kind of those domain information. And the last one, such as what the category of those objects included inside the images, for example, the dog, cat, and carp, this is also irrelevant to those domain information. And lastly, the most key and important component within this prompting engineering is that they try to come up with those domain-specific prompting, such as from the art, naturally will be including the creation, the painting, this kind of text. While from the clip art, mostly it's likely to be related with icon or illustration, this kind of words. So similarly, they will try to set up a bunch of this dictionary for these domain-specific words for to constitute the overall of those prompting text for them to provide a sufficient variances within the text input. And overall, the pipeline is like this. Similar as CLIP, there will be two major components. The first one is from the text encoder, with their novelty proposed of those prompting efforts from the domain agnostic context, domain specific context, and the class token kind of context, which is related with the class information such as dog, cat, fish, etc. And they combine this as the input to the text encoder, and eventually with those separation of those tokens, they will form of those text representations with each of those tokens, indicating each of those word, the keyword. And similarly, on the right-hand side of those image encoder, as the inputs, you can imagine that from the same category, but different domain of those params, as well as from different categories, but same domains of those plants versus the bike as the inputs in a whole bunch of, in a whole set of those batch size. And then further after this image encoder and text encoder separately, the operation will be staying in the embedding space. So we can see that they try to separate apart for the the visual embeddings for the same category but different domains separately. And then in this way, they will form a kind of confusion matrix or the correlation matrix to penalize the positive pair of those texts such as plan with the visual embedding of the plan representation together as the high score, while penalizing the different the negative pairs as the lower score. So in this way, they hopefully to learn a very representative embedding for both the text embedding as well as the image embedding. Of course, from their emphasis, they will be more relying on the image embedding learning while leveraging the original text embedding power, say, directly from the large language model and do a very local and small scale fine tuning with the text encoder. Another, very interesting and lying in this direction of leveraging the foundation model is this 3D human pose estimation. I will just utilize one slide to quickly highlight this kind of efforts. Like from their proposal, you can see that the novelty lies in that they will not only try to highlight the foreground of the hands, but also from their text depiction, they will try to highlight those backgrounds, which is from the text level, they try to encode the variances of those background into that, such as they come up with a different color of those background or from different scenes of those background. And in this way, they will try to encode this whole bunch of those encodings, including the variances from both the foreground and the background into their canonical of those pipelines of their branch 2 as their, the data flow of their architecture. So yeah, that's essentially how the large language model or the foundation model has been involved into several of those typical vision related tasks, such as the canonical object classification problem, as well as the 3D human posture estimation problems. This is so far for the perspective direction 1. For perspective direction 2, so we see that gradually, not only from the the canonical understanding of those visual embeddings or the visual scenes, there will be another kind of way, which is leveraging the causal analysis or causal inference to help for this domain adaptation and domain generalization. The causal inference is defined as that they try to analyze the response of an effect variable when the cause of the effect variable is changed. So there will be strong hypothesis that, say, for one of the observations, such as the domain A of those are actually categorized as object 1, something like this. So with this kind of setting, they propose a kind of causal graph. The traditional graph is actually only x to y, right? So which is a very canonical classification problem, based on the thematic feature of U in the feature space or in the latent variable space, right? So very novelly, they try to introduce this kind of selection of those source or target domain as a state variable. So essentially, they assume that the classification task X to Y is also affected by the unobserved semantic feature U, where U to X and U to Y denotes the definition process of semantic classes. Notice that these causalities have been shown valid in their respective areas. For example, U to X and U to Y can be image and language generation, respectively. In particular, the introduction of the domain selection variable S reveals that the fundamental reasons of the covariance shift and conditional shift are both due to that the conditional likelihood of given S to source domain or given S to target domain, the likelihood is actually shifted and appears to be different. Then how do this Yue and their colleagues and their co-authors to deal with this problem? The central idea is that for the causal analysis, they say what actually causes this to be appear with different domains. There must be this set of those interventions in between. Say, given the source domain of those images, there will be a certain kinds of those target domain images. What causes that? Maybe say, for example, the sketch lines might come from an original feature, original picture, but then you just extracting those lines and those edges there, then where you form those kind of sketches, right? So this might be that to edge file of those kind of original images will result in those sketch of the other domain. So this is just one example, and there will be multiple assumptions of those interventions ranging from M1, M2 until MK. And we call this as the causal factors. And the causal analysis actually is based on this strong hypothesis of those physical existence of those interventions. And they want to find out that from those assumptions, what are the most likely or the most probable of those interventions that indeed happens to achieve this kind of a domain gap. Once this is formed, they basically can utilize this and learn the interventions and further to reverse the intervention to close the gap from the source to target and from the target to source. This is the high level idea. And some kind of technical detail is that they try to set up this kind of hypothesis based on the Bayesian inference rules and assume isotropic Gaussian for the conditional probability, and there is a linear modeling of each of those feature space, feature embedding for f of y and f of x hat. Then the hypothesis of that x and x hat, the connection, the intervention between those two, actually can be mitigated by a kind of a linear operation that they have derived from their paper. Yeah, so this is so I would try to highlight that the causal inference actually could be one of the very important branch, because we know that to cause the domain differences, indeed there will be this kind of physical rules, but sometimes it may be hard to trace from the physical side. However, we can still from the statistical level to set up this kind of a causal relationship between one state of the variables to the other, and finally try to trace back about this kind of causal, the causal factors, and then try to mitigate those domain gaps, utilizing these newly found causal factors there. And the last direction is that from the recent coming literature, gradually we found that at least there are two major domains. One is the unsupervised domain adaptation. The other is the source-free unsupervised domain adaptation. We denote it as UDA and SFUDA. And from these two settings, one very typical difference is that from the setting, source-free means that during the optimization, the source data cannot be accessed anymore due to the limitation of those privacy concerns or kind of the access right of those data from the source domain, right? So from there, we compare the UDA and SFUDA from this literature that they have reported the numbers. One significant observation we have is that across those different canonical domain adaptation and domain generalization datasets, such as Office 31 and Office Home, as well as Vista 2017, we see that the UDA methods and the SFUDA methods, they actually are gradually at the same level. We know that SFUDA is more challenging because there is no any kind of those labeled source data to be utilized into the optimization or the domain adaptation stage, right? So this actually in the literature has long lasting to appear that the SFUDA will achieve inferior performance comparing to the UDA. However, in the most recent of those literature, gradually researchers has been showing that the SFUDA can approach at the same level of those UDA, or sometimes could be even slightly better comparing to the UDA. This actually brings us a very important observation and found that maybe source-free UDA has been showing a certain advantage over the traditional UDA, as well, given that the advantage that it does not necessary to access the source domain data. So which might be suggesting that we can gradually form up a kind of new training paradigms, such as at some kind of say combining those large language models from the pre-training stage, we might leverage those source domain data with the labels, with the labels or supervision in between. While after, when moving to the later stage for the model fine-tuning, we might not have the right to access the source domain data, and we can conduct the source-free UDA and combine with those large language models for the second stage. So there could be many more of other kind of new training paradigms for this domain adaptation and domain generalization. This is where we just bring up a kind of one of the very interesting finding and trying to inspire for the community that maybe this could be one of those very interesting direction for us to further explore and achieve even better results there. So far, that's pretty much the content that I would like to bring and share with all of the community members here. And feel free to raise your questions, and I would like to answer any of them, and also share your thoughts with us about your ideas and your opinions, both including the applications as well as the perspective for the future directions. Thank you so much for your attention. Any questions, please? If not, I assume I will try to hand back the time to Ronghang. And hopefully we can try to conclude from here and summarize more like during some kind of those offline discussions, or feel free to reach out to any of us through email, etc. So we would be more than happy to have the continuous, both the discussions and develop some of those potential collaborations with you guys. And thank you so much. So this is my sharing about the terminology.
Okay, I guess this will be the end of our tutorial. And dear audience, please feel free to check our website. You will be able to find out the revised slides of our tutorial, as well as a list of papers and other resources. Thank you all for your time and attention.
Thank you all.
Thank you.
And have a great upcoming CVPR.
Yes, enjoy.